Welcome to the Insightful Professor. Today's topic is patterns and expressions. In this video, we'll introduce two concepts. One is called pattern matching, where we construct a predicate used in a generic or similarity type of search for data that resides in the database. This capability by itself may have somewhat limited use. However, it further demonstrates the powerful capabilities inherent in relational database and SQL. The other concept you'll find to be of much more practical use. The other concept deals with deriving values from those stored in the database. This is accomplished through the use of what we're calling expressions. The majority of the examples that we'll present will involve arithmetic operations applied to the stored data to produce derived results. This topic is particularly important to understand because the manner in which values are derived through arithmetic operations must be understood to use aggregate functions, a topic that we cover in another video. All examples will involve a single table, but the concepts apply equally to multi-table operations. The examples will be presented using both Oracle Database and Microsoft SQL Server. So let's get on with it. Okay, what's the motivation with pattern matching? There are going to be times when we might want to retrieve some data from the database, but we don't have an exact value to provide. The predicates that we've used up to this point, whether they compared for a relational condition of equality or some kind of non-equality, greater than, less than, what happens is the value against which the compare is made or expressed in the predicate is always a very clear, very precise value. In this case, what we want to do, in order to be more generic, we define something called a pattern. The pattern is not going to specify or even know a complete column value in order to identify the rows, but it's going to do something kind of like a similarity match. We're going to say what I want kind of looks like this, and we describe what it looks like through our pattern. Now, the patterns serve, as I say here, to generically identify relevant rows to be included in the result set of a query or operated on by a DML operation. So if we're doing things like update, we might want to select, broadly speaking, a bunch of rows where we give a general characteristic that's used to identify or isolate those rows. Now, patterns apply only to character data. Keep that point in mind. So a pattern describes the characteristics of some character column. And we don't use a conventional relational operator, but we use this keyword that SQL provides for us called like. And this is where we get the notion of this thing is like this other thing, or it's similar to something else. So we specify the name of the character column, then the keyword like, and then a quoted string using single quotes or apostrophes, however you wish to refer to this. But within the pattern, we are going to include some kind of a character string, which typically is going to contain what we'll call wildcard characters or meta characters, which give us this, say, similarity capability rather than saying this is an exact value. Now, the characters are tipped off to the system as being meta characters or wildcard due to the presence of the word like. They kind of turn on the special power or special feature of these two characters that we'll examine. The two characters are the percent sign and the underscore. The percent sign, wherever it's placed, represents a string of any length, including an empty string, a string of 0 characters. So you're saying wherever you place the percent sign, there could be any number of characters that are present, or there could be no characters. But on either side of the percent sign, this is where we're going to provide something that kind of describes what we want. So some known characters, and then perhaps a percent sign to say, well, it has to start with this, and then it can end with anything. The underscore, on the other hand, is always going to be associated with exactly one character. So wherever it appears within the string that we're providing as the pattern, exactly one character must appear there. What that character is not important, but there has to be exactly one character in that position or relative position. So the wildcard character is also sometimes called a meta character. This is a term that's used with regular expressions. Now, pattern matching with the like keyword is not quite as powerful. In fact, it's nowhere near as powerful as regular expressions. Oracle and SQL Server, you'll see, do provide support for regular expressions, but that's another topic for another day. So let's get back to the concept of this pattern matching, which is kind of like a really trimmed down concept of what you might see with regular expressions. Our first example introduces the use of the percent sign. And again, the percent sign can be considered to match a string of any length, which includes an empty string, a string of length 0. So in this particular example, we're selecting some of the columns, course number and course name, from the course table. And we're doing this for those rows where the course name kind of looks like this little example or this pattern that we're providing. It starts precisely with I, N, T, R, O, and then comes our wildcard or meta character that says after these first 5 letters or these leftmost 5 letters, there can be anything, and I'll accept it because that's the generic pattern that I provided. So again, the where clause is always going to evaluate to true or not true, and when it evaluates to true, a row is returned. Let's go ahead and give this guy a try. Go into Oracle, and we'll say select course number, course name. From course, where the course name resembles, looks like, or is similar to I, N, T, R, O, and then anything after that. We fire it up, and we only have one such course, but I think it's sufficient to get the point across. We start precisely with these 5 letters, and that's what you see here. The percent sign says anything that follows that is acceptable, and we have several characters that follow that, so these remaining characters that I've highlighted would be considered a match to the percent sign. It turns out, once again, that the percent sign could be considered a match even if there were no characters, an empty string. So if we simply had a course that was entitled Intro, that would match this pattern. If we had a course called Introduction to Computer Science, that would match as well. As long as the first 5 characters are precisely what we've included in kind of the known portion of the pattern. And then we say anything after that is acceptable. And this behavior is exactly the same with SQL Server. I won't show all of the examples with SQL Server, but let's go there quickly just to show this one, just so we don't feel slighted. Okay, so here's the query in SQL Server. Same query. We're now going to fire it up and just show you what SQL Server does with it. And we get the same result that we saw with Oracle. Again, the behavior is identical. For that reason, I'm not going to show every query in both databases, but there will be some situations in this video where I will show you the query's behavior in SQL Server because it will be noticeably different. But with the pattern matching, there's not going to be a big deal to concern ourselves with. Okay. That said, the known portion is at the beginning, the unknown is at the end. Take a look at the second example. We kind of flip the situation around a bit. In this case, we're saying the known portion is at the end. We don't know what it begins with. Percent sign is up front, could be anything, but it must end precisely with CISM. So let's give this guy a try, and we'll discuss these 2 queries because there are some potential performance implications that you would want to consider. So I'm going to select the course name, from course, where the where the C name, like %CISM. In this query, I'm going to select the C name, the course name, from the course table, where the name looks like %CISM. That is, I don't know what it starts with, but it ends precisely with CISM. Fire it up and see what we get. We get empiricism and we get scholasticism. Both of these names end precisely with CISM. If we somehow had a course with the name of simply CISM, that also would have been retrieved using this condition or predicate, because the empty string, which would be thought of as preceding CISM, would be considered a match with the % sign. So if it started with CISM and there were no characters following that, that would also come back. Now here's an interesting thing to talk about. In the database, particularly with Oracle and with DB2, there is a clear distinction between fixed length characters and variable length characters. With fixed length characters, the data type of a column is defined as char. So what we have is CHAR means it's fixed length. So if we define a column as char length of 20, and we store a single letter or single character in that char field, then that character would be the leftmost character, and there would be 19 spaces or blanks appending to it. There would be trailing spaces or trailing blanks. That's important to consider because this alternative data type here of varchar is what is called variable length. And when you define a column of varchar, if you say varchar 20, you're saying this has a maximum capacity of 20 characters, but if the value that is to be stored is shorter than 20, only the characters that you provide in the actual value will be stored. So if you stored a single character in a varchar 20, only one character would occupy the storage out on disk. There would be no trailing blanks. Big difference in how these things are represented, but that also translates to a big difference here in terms of pattern matching. For example, this pattern here says the last 4 characters must be precisely CISM. Now, that's the case with the significant characters we've seen shown here for empiricism and for scholasticism. But clearly, these two names are not of the same length. So if empiricism and scholasticism, that is, if the C name values were stored in varchar, then the last 4 characters for empiricism would be precisely CISM, as would the last 4 characters for scholasticism. However, if C name was defined in the database as fixed length, then you can see that empiricism, if it's the same size as scholasticism, would have some additional characters after the CISM spaces to bring it up to that capacity of whatever the field is. Therefore, if C name was defined as fixed length, empiricism would not match this condition of the field ending precisely with CISM, because this field ends with CISM plus some spaces. So it's a subtle point, but that behavior is very important if you're working with databases such as Oracle and DB2. SQL Server is a little, I suppose you could say, friendlier, that you might, with a variable length field and a fixed length field, both retrieve empiricism and scholasticism, even if they are of different sizes. So it treats it a little bit differently. There's always these subtle little, let's say, nuances that you have to be aware of if you're working in a multi-database system. You could say that's kind of the fun or the thrill of working with database, but you could also say, well, that's kind of the annoyance of having these different systems or platforms. I like to think of it more in the positive sense. It's kind of fun or exciting. It's a challenge to remember all of these little subtleties. Hopefully you agree with that. Now, I said I was going to say something about performance here. Let's go back for a moment and look at this guy here. This is doing a search of all the rows, or potentially all the rows in the table that begin with INTRO. Suppose, for example, CNAME had an index created over it. What do you know about indexes? Consider an index in the back of a textbook. If you were to read the index entries from the beginning of the index to the end, what observation could you make about the placement of those entries with respect to one another? The entries are in order. It's in alphabetical order. So all of the words that begin with A precede all of the words that begin with B, precede all of the words that begin with C, and so on. It's in alphabetical order. So now, let's suppose you were to open up a dictionary and you look for the word introduction. You find it. But suppose you did this kind of a generic search called intro something or other. Then you would be brought to the place in the dictionary where the words begin precisely with INTRO, and you might actually see, perhaps, intro, and then you're going to see introduction, introductory. You're going to see a whole bunch of words, but they would be arranged in alphabetical order. At some point, you'll get something that clearly would not be considered a match, and you need to search no further. If you found a word that was spelled INTRP, then there's no need to look beyond that word because all of the other words are going to be greater than that, and they wouldn't match the pattern that's provided. So you could jump into the middle of the dictionary and do an efficient search. That's the same concept of what we see here with a notion of what's called query optimization and producing an execution plan. If the optimizer sees that there's an index on the CNAME column and you formulated your pattern similar to what we've done here, the known portion is the leading portion and the wild card, the unknown or variable portion, is at the end, the index could be considered for use by the optimizer, making the query's execution plan rather efficient. But on the other hand, this example, where we don't know what it begins with, but it ends with CISM, would cause the optimizer to reject the use of an index and do what's referred to as a table scan. Read every single row and look at the rows one by one to see if they satisfy the condition. The explanation as to why this happens should be clear if we think once again about all of the entries in an index of a textbook being in alphabetical order. Could there be a course whose name ends with CISM but begins with the letter A, begins with the letter B, the letter C, the letter D, and so forth? And the answer, obviously, is, yeah, there could be. Couldn't begin with anything. So therefore, you can't enter the dictionary and abruptly jump out. You have to look through potentially every entry in your dictionary, or hence every entry in your index, if you're going to use the index to do a search. And when you do value by value examinations in an index, that tends to be much more I/O intensive than if there's a way you could read bunches of rows or groups of rows from a table and perform what's called a table scan. So the general rule for behavior of a query optimizer in deciding an execution plan when you have a pattern of this sort, where the leading portion is a wild card or unknown, is to reject the use of an index on the column against which the comparison is being made, even if there is an index, because it will perform poorly. So a word to the wise on that. Okay, so we're looking at how to write SQL, but we also want to consider how to write good quality SQL that's going to perform well. But on the other hand, suppose you absolutely need to ask this question and get the answer. If you have a business case that justifies asking this question and incurring the processing overhead, the nice thing is it's a very powerful operation. If you can justify using it, go ahead and do it. Now, if you're dealing with tables like I have, 14 rows in the course table, not going to make a difference. But if you're talking about tables with, say, 14 million rows, 100 million rows, then you want to be cautious about using this. But the first form is quite acceptable. The leading portion is known. The trailing portion is the wildcard. Now we come up with another example. This example introduces the alternative wildcard or meta character. This one is the underscore, which we said accounts for exactly one character wherever the underscore appears. Now these things following the H, there are actually two underscores here. You don't really see a separator. It's underscore, underscore, but it looks like one huge line. It's not a big underscore on steroids. It's just two consecutive underscores and just looks like a big line. But it's one character for the underscore, then the H, then an underscore, then an underscore. Let's take a look at how this works. This is looking for an H precisely in the second position. And we account for the second position by saying there's something in the first position. I don't care what it is, but there's exactly one character there. Then there must be an H. Then there must be exactly two characters that follow. So let's go ahead and give this guy a try. Select CNAME, C department, from course, where C department is like underscore H, being in the second position, underscore, underscore. We're looking for exactly 4 characters. The first one, we don't care what it is. The second one must be an H. The third and the fourth, we don't care what they are. And notice we get philosophy and theology. And these values all satisfy or match the pattern that we've introduced, an H precisely in the second position. Here's an interesting little twist. We're not limited to using a single meta character, but if you thought about it, you could say, well, wouldn't it be easy to do this, and wouldn't it be the same thing? Well, it's easy to do this, and we get the same result. But is it the same thing? Technically, underscore H% is not equivalent to underscore H underscore underscore. Remember, in this pattern, we said there must be exactly 2 characters that follow the H. Whereas with the pattern where we have a trailing percent sign, there could be no characters, 1 character, or 2 characters. So the point is it's variable in length. So the 2 patterns are not identical. Keep that in mind if you're saying, well, it'd be more convenient to just type the percent sign and do it once. You may get a slightly different result. So keep that in mind. But this is also kind of neat that you can mix the different meta characters or wildcards together and formulate a very interesting pattern for data retrieval purposes. And we extend that notion with our next example. But the next example does something that looks like it's very verbose and kind of saying a lot. There seems as though there should be a way we can condense this. Remember, in our complex retrieval conditions video, we talked about the word in to create a list of values and to compare against the values one by one. It seems like this lends itself to that because all of the predicates here involve the same column, and they're all connected with or. It seems like a natural. However, it's the condition that's different that makes that an impossibility. Remember, in order to combine similar predicates with or and reduce it into an in and have a list and do what's called in-list iteration, what happens is the condition of the test is always equality. This is not equality when we use like. We can think of it more as similarity, not an exactness, but it's kind of like this, it resembles this, it's similar, it's not equal. So there is no way to condense this using the in because of the nature of in is always implied to be equal to this value or equal to this other value. Here it's similarity. But what is this guy doing? It's fun to take a look at it just the same. I'm not going to bother to run it. I think you can figure it out. But what we're looking at is there must be a character in the first position, and the values that we're providing that are known and must exist precisely within the second position. And then there can be anything following that. We are looking for all courses that have a vowel, the letter A, E, I, O, or U, precisely in the second position. That's what we achieve with this particular query. Now, probably not going to use this particular feature very often, but for completeness, let me mention one other thing. Suppose there's that off chance that what you're doing is you're looking for data in a column, and the data you're looking for, the pattern you'd like to use, actually is I'm looking for an embedded underscore, or I'm looking for an embedded percent sign. Well, there's a little bit of a problem here. If you were to actually go ahead and say, let's derive a pattern where we're saying that the pattern contains a percent sign, how do you make it a pattern? Well, you might say percent, 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 but then all 3 percent signs represent a wildcard, and you get everything back from the database, or everything back from the table. The good news is the rows you're looking for would come back, but you'd get all of the other rows as well. That's the bad news. So what you need to do is to kind of cancel out or neutralize this special meta character power or wildcard character power of the percent sign or the underscore, and make it just a regular, everyday type of character. If you're familiar with superheroes, you're probably familiar with Superman. And there was something that neutralized Superman's superpowers. That was called kryptonite. Well, they chose not to call it kryptonite in relational database. I think that's a flashy or sexier name. It would have caught on. But instead, they choose to use something called an escape character. That's kind of boring and ho-hum. But the idea is that by introducing an escape character and immediately placing the escape character before a percent sign or an underscore, you neutralize its meta character properties, and it becomes just a regular old run-of-the-mill underscore or percent sign, and then you can do a search for that. So it's not going to happen very often. If you're curious, put something in the comments section, and I'll give you an actual example. But just kind of knowing this is good enough. Especially if you're going to be on a trivia show like Jeopardy, this may be the winning answer. And if it comes out to be the winning answer in Final Jeopardy, send me a Starbucks card or something so I can get a cup of coffee, you know, your appreciation. Okay, let's move on. Numeric expressions. So that's it for pattern matching. You had a taste of it. I think that's ample coverage. So let's look at numeric expressions. Okay. SQL supports what I'm calling computational facilities that allow us to perform some kind of basic computations or calculations with the result that we retrieve from the database. We kind of intercept it, it's in the DBMS, but before it's returned to us through our front-end tool or through our application, we transform it in some way. We do some kind of manipulation of the data. We derive a result. And what I'm mentioning here is this approach could be very useful for formulating what might be called what-if questions, kind of hypothetical questions. Show me the current lab fee, and then show me what would the lab fee be if I increased it by 25. We don't have to retrieve both of these, but I'm putting them side by side so when I run the query, you can see what the original value was and what the computed value was to answer the what-if question. But in practice, we might say, give me the name of the course and show me the potential change to the lab fee if its value was increased by 25. What would lab fee plus 25 be? Okay, let's give it a try. I'm going to select the course name. I'm going to select the lab fee just for purposes of revealing what the original value is retrieved from the database. And then I'm going to add 25. And because it's a derived column, I'm going to give it a more meaningful or descriptive name. If I don't give it a name, what's going to happen is it's just going to become gibberish, may not be that meaningful to us. What did I do here? You need a where clause. Okay. I just wanted to make that point clear to you. If you weren't sure about the syntax, a where clause is definitely required when you introduce a predicate. Okay. So you'll see that every so often I intentionally make a mistake just to see if you're paying attention, but also to kind of make a point about something. Okay. And if you buy that, I've got a nice bridge I'd like to sell you. Okay. Now here we go. What we're doing is selecting columns where we're retrieving values directly from the database and also deriving a value. And then I'm renaming it because it's a derived value. So you can see the computation was performed quite quite nicely in that every value in the new phi column is exactly 25 greater than the values in the previous column, the lab phi column. And I'll show you this in SQL Server. It shouldn't really be necessary, but we'll go over there and show it to you nonetheless. And it's not necessary because the result is going to look identical. The only difference is SQL Server preserves the integrity of lab phi having been defined to the database as a decimal, so that's why you're seeing 0.00 after each value. And likewise, when the computation is performed, the result is also shown as a decimal. But the gist of what we have for output, it's the same thing. Now, while we're here, let's take a look at the next query. If you go back into the handout, you'll see that what I'm doing is I'm taking lab phi, and I'll show you this in a moment as we look at the handout, the presentation, and we see 2.375 multiplied by lab phi. This is where we'll note a difference between SQL Server and Oracle. When we go ahead and fire this up, what happens is we had a 2-digit decimal value in lab phi, and we multiplied it by 2.375, 3 digits to the right of the decimal point. The result is every value is shown with 5 digits after the decimal point. So there's consistency with respect to how the values are rendered or displayed in the output. That's the difference that we see in terms of presentation. Let's take a look at this query and see its output when we put it into an Oracle database. The values are the same, but they're not represented with the same precision and scale in terms of how this particular front-end tool renders it. If we were to use other tools such as SQL Developer, then you would see more consistency with the way the output is presented. But the values are the same, and that's really what's important here. So the result data type. Let's discuss this in a bit more detail. What we have is numeric value expressions allow us to perform operations such as addition and multiplication that we've already seen, but also subtraction and division. So all 4 basic arithmetic operations are available to us as we describe our expressions and what the derived value will be, or how it will be computed. Any numeric data type can participate in the expressions. We've been using integers and decimals, but we could use any data type, such as floating point, for example. So SQL Standard defines the rules for the data type of the result of the computation, and these rules are based upon the data types of the operands participating in the relationship that we're expressing, or in the expression that we're computing. Here's the general principle as stated by the SQL Standard. If any approximate numeric type participates, the result will be of some approximate numeric type. What do we mean by approximate numeric type? Take the value of 10 and divide it by 3. What is the answer? 10 divided by 3 is what? Well, if you gave me a complete answer, you would say 3.333, and you would never stop, right? Because no matter how many 3's you put after the decimal point, you never quite got the right answer. So at some point, for representation purposes, computers choose to approximate such numbers. So 10 divided by 3 cannot be precisely represented within the computer. It's approximated. So things like floating points are approximate data types. And what this first statement says, if you have a floating point involved in a computation, the result is likely going to be some floating point number. Maybe it be single or double precision, but that's not critical. The point is it's going to be an approximation because an approximate value or data type participated as an operand. On the other hand, we have this thing called an exact numeric. We can exactly represent values like 1, 2, 3. We can represent integers precisely. We can represent decimals precisely or exactly. So if both operands are of an exact numeric data type, the result will also be exact numeric. And if the operation is division, the result will be defined by the particular implementation, whether that be DB2 or SQL Server or whatever. So they're not necessarily going to be consistent, but it will be represented as an exact numeric. This raises some interesting points if we were to do some kind of computations with the different data types. So let's go back to the database and take a peek. We've already looked at this multiply, and we saw how that worked, that it did have a value that was shown differently between Oracle and SQL Server, but the essence of the values were the same. So again, that's kind of implementation dependent. Here's another little twist. We're going to do a subtraction, and we're going to show you that simply the result of subtraction could yield a negative number, and the system will show a sign. Okay, let's take a look at the query then. We're going to select the course name, the course lab fee, the course lab fee minus $25.75, and recall that we have some lab fees that are smaller than that. We have 0 lab fees. So what's going to happen for those is a minus sign will appear in the value for those rows. So the front-end tool makes that clear to us. We'll select these values from the course table and limit it to the rows for CIS. And when we do that, sure enough, we do see negative numbers in the result highlighted with that minus sign. Now, let me show you something where we're talking about the numbers and the accuracy. Let's suppose I say I'm going to select, and we'll select a literal value. We'll select a value of, say, 10 and divide it by 3. And I'll select this from the course table. And because I only want this to be done one time, I'll include a where clause that says that the course number is equal to C11. The where clause will identify exactly one row, so this select will be evaluated exactly one time. And notice we get 3.3333, and it's one of those floating point or real numbers. I'm going to take the same query, and I'm going to go over to SQL Server. And when I fire this one up, I get a little bit of a different answer. Instead of 3.3333 and so on, what I get is 3. The reason is that 10 is an integer, 3 is an integer, and what we have is a case when you divide an integer by an integer, the result is an integer. This is the behavior you see with SQL Server. The same behavior is exhibited by DB2. But Oracle, when it extracts a value from a database column, it doesn't remember the data type, it just treats it internally as number. Oracle respects the data type only when you preserve a value by storing it in a column. Here the values obviously were not extracted from the table. They were just introduced as integer literals. Here's an interesting point. Suppose I make it 3.0. Now I'm dividing an integer by a decimal. And this changes the whole set of rules. The game is played a little differently here. Now I get 3.333. We'll look at the principle of what's going on here with a special operator that SQL supports called the cast operator, and examine this in a bit of detail where we'll do what's called explicit data type conversion. So anyway, it's kind of a funny thing, but this is going back to the statement I made about the data types and how respectful the systems are of exact numerics versus approximate numerics, and then what happens when you have a couple of exact numerics or a couple of approximate numerics. What will the result data type be? So this is an important point to consider if you're going to be doing arithmetic of this nature. Now, we're using the arithmetic within the select clause. But if we were to do an update operation and alter the value of a column within a table and looking at some existing row, we could also be using arithmetic expressions of this sort. So these expressions are not used exclusively for data retrieval. You could see these expressions being used in what's called the set clause of the update statement, in which case you're saying put this thing, compute it first, and whatever it is, put this thing, the result of the computation, into this column. And that's where the data types will again become an issue. It's pretty important to consider that. Now the next example is a bit different than the one we just showed. We divided a literal by a literal. Here we're dividing the value of one numeric column by another numeric column. Now notice this expression is going to be evaluated not once and we're done, but once per row, because it's deriving a value that will be displayed in the column that I'm calling ratio for each row of the result set. So for each row that comes back, and in our case there will be 6 rows due to this predicate because we have 6 courses sponsored by CIS, there will be computations performed 6 times, once for each row. The principle of what I was just saying about the data types applies here as well. Let me show that to you. Let's select the lab fee divided by the credit, and we'll call that ratio. And we'll select this from the course table, and we'll limit it to the CIS-sponsored courses. Now, lab fee is a decimal, credit is an integer. Very similar to what I did a moment ago when I said, let's take 10 divided by 3, but then I said 10 divided by 3.0, and I introduced a decimal. It changed the whole set of rules. So we have a decimal here and an integer. That's why we get a decimal result. But suppose, just suppose, both of these columns were integer. Then this would be an integer divided by an integer. What would the result be? It wouldn't be a decimal. It would be an integer. So I can't use the same little trick I did earlier. I can't simply go, oh, credit 0.0. That doesn't make any sense. And you can see SQL Server starts getting upset already. It has these little red squiggly lines that says, whoa, I'm totally confused. What are you doing? This doesn't make any sense to me. So you can't do that with the name of a column. See, credit is an integer. Lab fee is a numeric or a decimal. So we don't have to worry about it. But if they were both integers, that rule doesn't help. Okay, that principle doesn't help. So I've got another way to do that, and I'll show you that in just a moment. Okay, one other point that comes up whenever you're doing arithmetic is the order of evaluation, or the hierarchy of the operators, or what I'm calling operator precedence here. What happens is, if you have a combination in a complex expression of addition and subtraction and multiplication and division, then left to right order doesn't determine the way things are going to be evaluated. Operator precedence comes into play. If you have two numbers being multiplied, even if that's not the first operation you do, that would be a higher precedence than doing addition and subtraction, so that would be evaluated prior to doing the addition and subtraction. So let's take a quick look at the behavior of this. Multiplication and division operations will be evaluated first in a left to right scan of your expression. Addition and subtraction operations are evaluated also in a left to right scan of the expression, but after the multiplication and division. And then the order of evaluation could be altered by taking expressions or sub-expressions and enclosing them within parentheses, kind of raising the precedence of what's going on. We do what's in parentheses first and work our way out. So the next slide offers an example where we can discuss this point. We're going to add a value of 25 to the lab fee, and we're going to do division. If we did not have parentheses, the division has a higher precedence, and we would divide the 25 by credit and then add the lab fee. but we're forcing the addition to be evaluated before the division. It's lower operator precedence or lower in the hierarchy, but it gets evaluated first because we're forcing it along that line by using parentheses. Let's confirm that behavior. Okay, so there are my columns that I'm selecting, and I've got my expression, and I'm forcing the addition to be done before the division. And I'm going to select this from the course table, and again, simply target the row sponsored by the CIS department. So the point is the lab fee had added to it 25, and then we divided by the credit after doing the addition. So what does that mean? We have 125, and we divide that by 3, and we have 75 divided by 3. 0 plus the 25 is 25, 25 divided by 3, and so forth. If we modify the query just slightly in terms of what we're writing, but significantly in terms of what the result will be, we'll remove the parentheses, and now with this expression, the addition reverts back to its lower priority, not going to get done first. We'll do the division first, so we'll divide 25 by 3 and then add that to lab fee. Well, remember up here, this is the effect of 25 divided by 3, 8 point and a whole bunch of 3's after it. So let's see what happens. So now we take whatever the current lab fee is and add to it the result of the division, which we had noted was 8.3333 and so on. So now you've got 50 plus 8.3333. There you go. 100 plus that 8.333 and so on. So clearly the order in which the operators were applied or evaluated has changed. It's now the default operator precedence. Let's return to our presentation and see what else we have. On the next slide, we are again doing lab fee divided by credit, so that will be done once per row to present the result to be displayed. But this query shows another application of an expression. There's a predicate added here in our where clause that says, do the computation, divide the lab fee by credit, and if the result of doing the division produces a value that's greater than 30, then this condition is true and the row will come back. Think about what has to be done here. How are you going to know if the lab fee divided by the credit produces a value that's greater than 30 without doing the division, without performing the operation? You can't really know it. So what this means is it would be necessary for you to, if you were the query optimizer and produce this execution plan and then you're following the execution plan, it would be necessary for you as the DBMS to actually retrieve the row, examine the lab fee from the row, get the credit, do the division, and then determine the status of that row, whether it's preserved or discarded. That is, whether it satisfies the predicate. Hopefully you see what I'm saying here, that this means that if you have this type of expression, the only way you're going to know if this is true or false is to actually read the row, even if you don't want to pass it on to a user in the result, because you need to obtain the lab fee and the credit to do the division to assess the predicate. That's a lot of overhead. Oracle is kind of interesting here in that Oracle, if you saw you were going to be doing this a lot with your data, you could create what's called a function-based index. You can create an index not over lab fee or not over credit, but you could actually evaluate the expression of lab fee divided by credit, and that becomes the index entry. So there's overhead, and there's some other requirements to set this up in an Oracle database, but this is what is referred to as a function-based index. You could actually have the system evaluate the result of this expression and create an index using that result as the index key or index entry. Then subsequently, when you form a query, as I'm doing here, and use that exact same expression, the system said, hey, I've seen that before. There's an index for that expression. I can use the index, and I don't have to compute the expression for each row. I can determine which rows have the result of evaluating the expression greater than 30. Because I already did that. I did it in advance. Very often that technique of using a function-based index is going to be seen more in a decision support or data warehouse environment than in a transaction processing environment or an operational data store. Yet it is still possible that you could encounter it. So it's kind of interesting. So my general statement here regarding this would be, don't do this kind of stuff if you have very large tables and you're just saying, well, it's kind of convenient to do it this way, because there is the potential for a lot of additional overhead. Table scans might result, and if you've got millions of rows, instead of being able to find the data that you want quickly or efficiently by using indexes, the system kind of has its hands tied in a sense that the only recourse it may have to evaluate the predicate is to do a table scan and read all of the rows in the table. So be very, very careful in using this. I would think twice about using it and make sure you're not going to create some problems. In this case, that predicate is used together with C department equals CIS, and because both must be true, there would be a little less pain in using this. Some of the sting would be taken out because this expression would be evaluated only for those rows that satisfy this condition of department being CIS, and those rows could be identified through an index. So it might kind of lessen the burden on the system, but nonetheless, it could add some additional processing overhead, and you want to consider that. Now, we have a topic here called sorting by a calculated column. So what happens if you retrieve a value that is derived and you want to impose an order on the rows in your result set for display purposes or for processing purposes, such that you want it ordered by that derived value? Well, this example is a little odd because what I'm doing is I'm retrieving the actual lab fee and then lab fee plus 25. So if I ordered by lab fee, it's the same as ordering by lab fee plus 25. It's going to be the same ascending sequence. But remember, you don't necessarily have to retrieve this column that you use within the expression. So suppose I retrieve the name and then the lab fee plus 25, but did not retrieve lab fee by itself. Then I wouldn't have the luxury of referring back to this column. So here I have a few different ways that I can identify the row for imposing an order. I can use the position that the row column appears, or I should say the column, not the row, but I can use the position that the column appears in the left to right display sequence. C name is listed first, then there's a comma. C lab fee is the second column in left to right display, then a comma. C lab fee plus 25, which will be renamed as new fee, that is in the third position left to right, third column in the select list. So the order by says order by 1, 2, 3. This is column 3, order by the values in the third column. That's one way of doing it, order by the third column. Now, that's convenient because you don't have to worry about how else would I make a reference to this. But there's also a potential side effect here. Suppose this query underwent some maintenance, and between C name and C lab fee, a couple more columns were inserted. Then the third column in the left to right display would no longer be making a reference to this derived value here. It would be referring to something else. So that's one little caution in using this approach. There's a second option. The second option would be I could say order by and use this actual expression that was used to do the computation and derive the value. So order by lab fee plus 25. That will work. But perhaps a better way is to say order by and use the name that's been assigned to the column. This is another reason to apply the rename, so that you're guaranteed you have a convenient and consistent way of referring to the column. So we could say order by new fee. A general rule here when you make a reference to a renamed column is if the column is enclosed within the quotation marks as you see here, or what programmers call double quotes, you should make a reference identical. Order by, quote, new fee, quote. Keeping in mind that once you use quotes, everything you use between the quotation marks is case sensitive. So if you spelled it all uppercase here in new fee and used it down here and spelled it in mixed case, they're not going to align. You may have problems. Some systems will kind of gag on that and give you an error. But anyway, there's the third option. So 3 options for ordering the result or sorting the result set. Now, the final expression shown here does not involve arithmetic. It's kind of a string or character type of expression. Here we have an operator which is defined by the ANSI SQL standard, 2 consecutive vertical bars. So if you look on your keyboard, what you'll see is probably right above the Enter key, there is a solid line of some sort. That solid line is what you have here, but 2 instances of it. So you would say select C department, vertical bar, immediately after that a second vertical bar. 2 consecutive vertical bars defines by the ANSI standard a concatenation operator for strings. So it will effectively take one string, C department, and add to the end or append to it C name. This is why I call it kind of a string addition. So I suppose you still could kind of stretch it out and say it's numeric. I'm adding one string to another. But it's not taking the values and producing a numeric result. It's appending. So kind of adding on to the end, that kind of addition. And I'm doing it here with just a subset of courses. Let's take a look at how this works in both databases. Okay, so in Oracle, I'm going to start off by saying, show me the department, show me the name from course, where the credit is equal to 6. And we see the 2 distinct columns shown here. Now I'm going to make the modification to perform the operation presented in the handout. I'm going to take the C department, vertical bar, and then I'm going to take the course name. Because this whole thing is a derived value, I'm going to give it this real fancy name of new string from course where cred is equal to 6. And notice what you have is you have Phil solipsism, Theo communism, and they're just now these long strings put together as a single string. That's what concatenation does. Okay. Now I'm going to go into SQL Server and give it a try here. And a very strange thing happens. I just enter it in. I'm using a version of SQL Server 2012. I think I've tried this on some later versions as well. But this is an ANSI standard feature. And notice there's this little red squiggly that you see here. Vertical bar, and then the second vertical bar has something under it. It doesn't like that. It says incorrect syntax. It doesn't recognize this symbol. Isn't that odd? This is an ANSI standard operator. How can it not recognize it? Well, depending upon the version of SQL Server and whether you've got compatibility mode set or whatever, what happens is it has its own way of doing concatenation, which is a bit odd. What it does is it uses the plus sign. Now, we've seen the plus sign already for doing other things. What did we use the plus sign for? Exactly, to do addition, to add 2 numbers. But here, we're taking 2 character strings and kind of adding them. Well, what we're doing is appending. So I guess that's another argument for saying it is string addition. But this leads to some potential problems. Let's go ahead and try this. And now we do get the concatenation. So be aware that the concatenation operator defined by SQL Server is actually a plus sign. Now, I haven't tried out the latest versions of SQL Server, but I also haven't tweaked the system to adjust parameters. But basically, just an off-the-shelf type of install, this is the behavior you're going to get, a different operator for concatenation. But this raises an interesting issue. Let me go back to Oracle for a moment. Isn't it fascinating how everything I talk about in the database I perceive as being interesting? There's nothing boring about database. It's all interesting, exciting stuff. Okay, hopefully you have a little bit of agreement with that at least. Let's go ahead and say what I'm going to do is select the course department and the course lab fee from the course table. Now the difference here is naturally that C department is a character string and C lab fee is a number. Concatenation is a character string operation. Look what happens here when I say select C department, concatenate C lab fee. First off, you might say, well, wait, whoa, that doesn't make any sense. You're taking a character string, you're doing a string operation, but the second operand is a number. Okay, just sit back and enjoy. What happens is the system's going to help me out. It's going to take the lab fee, which it knows is a number, but can't be used as a number with this operator of concatenation. It will do what's called an implicit data type conversion. It says, well, lab fee has to be a string in order for this to work, so Oracle generously converts it to a string for me. And that's the exact same behavior with DB2. So I select this from the course table, and I again restrict the result to 6 credit courses. So notice I get the concatenation. It first implicitly converted lab fee to a character string and then performed the concatenation of those 2 strings. That's kind of neat. Now, let's go over to SQL Server. And remember, we'll have to modify this query because it's not going to like the 2 vertical bars, so we're going to do the plus. So now, with the plus sign, let's see if the behavior is the same. We want to take a character string, and we know that this means concatenation. And here's a number. Let's see if it helps us out and converts the number to a character and proceeds with the concatenation, as Oracle did. Ooh, it didn't do that. It says error converting data type varchar. Remember, that's a variable length character string to numeric. It tried to go the other way. It tried to take this guy here, which is a character string, and convert it to a number so that it could interpret this operation as addition, not as concatenation. That wasn't very nice. Why didn't it go the other way? The other way it should work. But here it says I'm trying to take your character, make it a number so that I can interpret this as addition. This operation of plus is overloaded. It has 2 different definitions. It serves to do both concatenation and it serves to do addition. The context, that is the nature of the operands, determines how the system's going to interpret it. If both of the operands are numbers, it will do addition. If both of the operands are characters, it will do concatenation. But when we mix it like this, the implicit data type conversion that we saw done very nicely with Oracle doesn't work so well here because it goes the other way. It's biased toward this plus sign being addition rather than concatenation. That's not very good. So, how do we get around this? Well, there's a special operator that we're going to take a look at called the cast operator. Rather than relying upon implicit data type conversion, we're going to have to tell the system what we want done explicitly. And that's accomplished by using that special operator that I've mentioned called the cast operator. So the cast operator is actually defined in SQL as a function. You'll see that there's use of this within Oracle, but perhaps it's much more widely used with database systems like DB2 and SQL Server, where they're much more respectful of the exact numeric and approximate numeric data types. So it's more of an issue with those database systems. But here's a variety of things you can do with it. And I'll let you read this. You can pause the video and check it out. I'm just going to continue. I'm kind of pumped up. I'm excited about this. Okay, so here's how the cast function works. A cast expression is formed according to this syntax. You'll use the word cast, and because it's a function, you have parentheses where you'll pass the argument, the thing that's going to be manipulated. So we'll pass the name of the expression or the column that's going to be altered, or whose data type will be treated in a different way. Not really altered permanently in the database, but treated in a different way. How do we want to treat this expression or this column? We want to treat it as though it were some other data type. So here we're going to take the salary, which is numeric from the staff table, and we're going to cast it or treat it as though it were a character string. Now I'm going to run this with Oracle because you can get a visual confirmation that something is really happening here. You'll have a similar effect with SQL Server, but it's not going to be as exciting as what you're going to see here. So I'm going to select the salary, the numeric column, so I can see what's in there. Then I'm going to cast that numeric value as a varchar length of 15 to make it a character string, and then I'll give it a descriptive heading. And I do this, this is from the staff table. This is why I wanted to do it with Oracle, because Oracle shows numeric data right aligned. So you can clearly see the salary is numeric. It shows character data left aligned in the display of the column. So you can see that what we're showing in what's called salary is not numeric. It's been converted to character. You can confirm that with this visual confirmation here that it is left aligned versus right aligned. It's a different data type. So I think it's a little bit more exciting to see it with Oracle. But the concept of what happens is transforming the data type. It happens in the other system as well. So let's go over to SQL Server then and see if we can fix our problem. We want the plus to be interpreted as character data. For the plus to be interpreted as character data, we must take any numbers out of here and treat them as character. So now I have a character value for the lab fee and a character value for the department, and now we've accomplished our concatenation. So this is called cast, but it's also referred to as explicit, data type conversion, because we have to tell the system to do it. The implicit conversion fails here. It's kind of like, I'm crossing my fingers. I hope it does what I want, but when you do cast, you don't have to worry about it. It's going to do what you tell it to do. Got another example in the handout to show you a subtlety with the cast expression and cast functions. Here, it's a timing issue. If we take this query, we're taking credit divided by 2. 2 we know is an integer, credit is an integer, and when we run this in SQL Server, you're going to get integer divided by integer. The result will be an integer. 3 divided by 2 will be 1, not 1.5. So we try to use the cast operator and say, well, take the credit and divide it by 2. Oh, and what we'd like to do is convert it to decimal. See if we can get away with that. Let's see what happens here. So we have select cred divide by 2, kind of let the chips fall where they may, and then we're going to say cast cred divided by 2 as a decimal, and give that the title of cast after, and then we're going to select cast cred, convert that to a decimal, and then use that converted decimal and do a division by this integer of 2. And we select that from the course table. Okay, fire that up, and here's what happens. The first one, cast after, said take cred divided by 2, and it would seem as though the as decimal should have an effect. But what it's doing is it does a straight left to right scan, evaluates the expression, but it doesn't give me the decimal effect I'm looking for. So what we have to do is we have to make sure that the individual operands, at least one of the individual operands, is of a decimal or floating point value in order to achieve this result here. So I first convert credit to decimal, then with that integer treated as a decimal, that's what CAST will do, I then do a division by a real integer, and the result is what I was hoping to get, 1.5. So the point is, in order to achieve the same result that I would get with Oracle, I have to take this other step and do the explicit data type conversion with the CAST operator. So again, this is one of the joys of working in a shop or in an organization that has more than one database management system, and they might have some differences. So you have to be aware of some of the subtleties or behaviors of these different systems. So hopefully you found that useful and informative. I found it exciting. Now, here's a whole nother area. This is pretty wild. Case expressions. What happens here is we have the ability to inject within our SQL statements conditional logic. Remember, SQL is essentially a non-procedural kind of descriptive or declarative language to describe what the output looks like, but it doesn't say how to do it. In a sense, we're injecting a little bit of processing in here. This is part of the data manipulation. It's kind of if-then-else logic. Conditional logic is part of what we're going to see happening now. Here's where this might come into play. Suppose you have values that are stored as integers, kind of representing some encoded value. Integers don't take up much space on disk, but what you'll see is if you store character strings, a single character string could be 15, 20, 30 characters long, and if you have that occurring many times, you end up consuming a lot of disk space. So sometimes what you'll do is you'll store data values encoded, but those encoded values have to be decoded or interpreted by a user. And to make it easy, we can do it within the SQL and retrieve the encoded value and decode it before we present it back to the user as output on the screen. Now, I've had instances to do this. I did a consulting job for a manufacturing company, and I found a good opportunity to do this. I did a consulting job for the U.S. Navy, and I found a good opportunity to do something along this line. And it works so nicely to do that kind of interpretation of the values, because you're saving storage and performance, reducing the amount of I/O to get your data, so you're getting more efficiency there, but you're using a couple of CPU cycles to interpret it, but it trades off very nicely and becomes beneficial. Now, to do this, we're going to look at this special expression called a case expression. Keep in mind my point here, that this is not a case statement. Many languages, if you've worked with programming languages in other environments, will support a case statement. Case, as it's part of SQL, is an expression, not a distinct statement. Because it's an expression, it can be embedded within statements like select. It could be embedded in statements like update and so forth. It can be embedded in other SQL statements because it's simply an expression, just like lab fee times 2, for example. So that's very powerful. There happen to be two forms. Technically, we don't need both forms. We don't need both a search case expression and a simple case expression. But because SQL was produced by a standards committee, if someone suggests doing it one way, they're going to say, okay, we'll do it. We don't want to make any waves or have any problems here. I guess you think it's a good idea, we'll do it. I mean, that could be the rationale, and I think often that's what happens with standards. But we really don't need both searched and simple. I'll show you search, show you how powerful it is, and then I'll show you this maybe a little easier form, the simple case expression, but it's not as powerful as the search. But you may encounter both flavors of this if you're reading someone else's code, so you at least have to understand the simple case expression syntax, even if all you do is write case expressions using the search case expression syntax. here's the syntax for search case expression. Notice there are delimiters. You start off here with the word case to introduce, and you end it with the word end. So between these two delimiters or these two boundaries, this is where you find the body of the case expression. So this could be rather lengthy. This could be 50, 100 lines of code or so within a SQL statement. But the idea is, regardless how much code you write here, the end result is this will become exactly one value in one column for a row. So you can have 100 lines of code here and end up with just one value in one column for each row. So no matter how simple or complex the expression is you produce, it reduces to just one value. So you've got to keep that in mind. But basically, you're writing some code here to go through the process of deriving that value. So here's how it behaves. What you've got is you've got a when, and each when will have associated with it a then. The when introduces a search condition. The then says, if this search condition evaluates to true for the current row, then produce this result as the output for the case expression, and I'm done. So the point is, it's going to go in this direction, top to bottom. So the order in which the search conditions are listed is going to be significant, because it is possible that for a particular row, more than one of the search conditions that you express in the case expression could evaluate to true. But doing a top to down or top to bottom type of scan, the first one encountered that evaluates to true is the one that determines what the value will be, or the result will be, that is returned for this case expression and will appear in the column. So we can list a whole bunch of these things. Now we can go through the whole list, and it's possible that none of the search conditions are satisfied. None evaluate to true. In which case, the default behavior would be that the entire case expression produces a value called the null value. And the null value is discussed in a video called Missing Information, if you want to see a detailed discussion of that. So if we don't find any matches in the whens, then we return a null value. To address that special situation, we can include kind of a catch-all. When this, return this. When this, return this. So it's kind of an if-then-else. But if none of the whens evaluate to true, we can say a final else clause that says, well, if none of these are true, else, and here's the value we're going to return. So that's if none of the whens are true, we can put that in there. But if you omit that, and notice I have it in square brackets to indicate it's optional syntax. If you omit that, then you're going to get a null value as your result or your output. Okay, that's the background. Let's get ready to take a peek at this in action. Now that we've seen the syntax, let's see a query. In this particular query, we're selecting 4 columns. Let's see if we can find just where those 4 columns are. We're selecting CNO, then there's a comma. So now that's the first column. CNAME, comma, there's our second column. Case, a couple of when, then clauses, end, and here's the comma. And we're doing a rename because the case expression is deriving a value. The fourth column is C department. One of the main reasons that I've selected 4 columns here is I wanted to situate the case expression, which you see is very large in contrast to the other columns in terms of how you express what the value will be, because you're writing basically a little code here that says if then else. So I wanted to place that case expression between 2 columns to show you that it does not have to be the last column or the first column. It can be situated anywhere. And that's the reason I chose to select department as well and also have it be the last column. So what does this case expression do? What this is going to do is going to take the credit value, because remember we are retrieving rows from the course table. So it will take the credit value from the current row being considered. And if the value is equal to 3, And again, there's no where clause, so every row will be processed. But if we had a where clause, it would then look at the credit for only those rows that satisfy the predicate. So if the credit is equal to 3, it will return a value of THREE. It interprets the number and shows it as a character. It's a transformation or a decoding, as I was suggesting earlier. However, if the current row does not have a credit of 3, but the credit is equal to 6, then it will return the character string SIX. If it's any other value, null will be returned. But given the current content of my database and the current, say, business policy or business rule at this school, you can only have 3 credit or 6 credit courses, so nothing else will appear. We'll address the situation where you might have another value and you've not taken into account all possibilities in just a moment. Well, let's see how this works. And again, I'll do this in Oracle for, I think, a better presentation. We'll select the course number and name. The case expression could appear anywhere, but I happen to just put it on the next line and then indent. Indentation is not required, but it's probably good practice to make it more readable. So when the value of credit is 3, we return THREE. If that is not true, we get a second chance. If the value of credit is 6, then we return SIX. And we're going to give it a name of credits. And then we add one more column. And again, just to show you some variation, I had put the C department on a separate line, but I could just continue here. Might not be as readable, but the syntax is flexible. And I select this from the course table, so I get all rows. Now, this is showing us the 3 and the 6. Probably makes sense, but just to be safe, I'm going to modify my query just a little bit. Why not show the actual numeric credit? That's what I'm going to do. And that way, we can get confident that we are getting the transformation occurring properly. There we go. Okay, so for those rows where we have a value of 3 in our numeric column, we get THREE. For the couple of rows where we have a value of 6, we get SIX. It worked as advertised. That's always nice. Now, take into account another situation. The next query says, well, what happens if you're testing for 3 and you don't get that, but then you try for 4, and what happens if you don't get that? Well, we don't have an else clause here, so what's going to happen is we will get null. And remember, we're going to have 3 credit and we're going to have 6 credit. We're never going to encounter a 4, but when we encounter the 6, it's not been explicitly identified for a test. Therefore, we're going to get null returned. And likewise, in this case, I also did not rename. So we'll run this through as you see it here. Select course number, course name, and I'll select the credit once again. Case, when cred equal 3, then THREE. When cred equal 4, then FOUR. End, and then C department from course. So a couple things to note here. First off, when we had the value of 6, that was not one of the values for which we put an explicit test, and there was no else, therefore the null value got returned. Second thing to observe is the column heading. I did not do a rename. Notice the actual expression that was used to produce the result is very lengthy. It didn't use all of that. The column happened to be only 5 characters in length to display the longest or widest value within the column, so the column heading was shown as only 5 characters, which would be the first 5 characters shown in this entire expression. You can see why I've been encouraging and stressing the importance of renaming, because here, what is the expression that's used here? What is the meaning of this column? It's not at all evident from this truncated or abbreviated column heading generated by the front-end tool. So therefore, renaming whenever you have a derived value is actually very, very important. Okay. Now, if you're not impressed with case yet, I'd be surprised, but in the event that you aren't, look at what else you can do here. Just like you can have an if statement in a programming language and have an if nested or embedded within another if, you can have a case expression nested or embedded within another case expression. Here we have the major case expression where we're saying case, and I've highlighted this in a different color, so you can see it encompasses almost all of the code I have here is the primary case expression. We have a when clause that says when the credit is 6, then take some action, else do some other action. So when credit is 6, what does it do? It does a nested case, a second conditional check. So if credit is 6, I'm going to inspect the row a little further. I'm going to say, oh, the credit is 6. Well, what about the lab fee? If the lab fee is greater than 0, then I return 6 and say not free. I know it's 6 credits, otherwise I wouldn't be within this nested or embedded case expression. Now I'm testing the lab fee. And down here I see, well, the else clause says the lab fee is not greater than 0, but we know the credit is 6, so I say 6 and free. And finally, if it's not 6 credit, then I come down here and take my alternative path and say, well, what about the lab fee? So I can tell you it is not 6 credit, and it's not free because the lab fee is greater than 0. Else, it's not 6 credit, but it is free. So you can kind of walk through that logic, and hopefully that makes sense to you. Very powerful capability because of the ability to nest this conditional logic. So case expressions can be nested or embedded. Okay, we've talked about the result being produced, but we haven't been very clear in stressing a very important point that the ANSI standard makes. The data type of the result values of a case expression have to be what is referred to as union compatible. Well, think about what union compatible might mean. What happens is union compatible says you're taking the output of your first when, so the then is going to be of a certain data type. But if that doesn't work, if that's not true, you take the output of the second when, take its then, and that may be the value that is returned. The point is that all of the then clauses have to produce something that would be of a similar data type, because regardless of which path through the conditional logic we take, the same type of thing has to be returned, because all those things that are returned in evaluating the rows through a case expression will be deposited in the same column. So you can't have some things returning character strings, some returning floating point, some returning dates. It doesn't make any sense because all those things have to go into the same container, the same column. They're all going to be deposited into the single column associated with wherever the case expression appears within the select clause. So, broadly speaking, all of the values produced have to be in the numeric family, or all of the values produced have to be in the character family, or some general data type family. You just can't mix and match. Furthermore, the ANSI standard has dictated that they don't want you to do implicit data type conversion. Even though vendors we know can do that, the ANSI standard says, no, that's not the way we want this to be implemented. So if you want our blessing and get our compliant label, then you cannot do implicit data type conversion. You must make it clear as the output of each then clause must be clearly stated as being the same data type. Now, we already saw some potential problems with implicit conversion, so that may be one of the things that the ANSI standard folks had in mind. So the data type of the case expression is going to be determined by union data type rules. Union, where we're looking at union compatibility, it turns out that union itself is a special SQL operation. It's a multi-table operation. We'll discuss that later on. So here's your first peek at this term union compatible. You're going to see that more if you watch the remaining videos that we post on the channel. Okay, excuse me. One more thing. We had emphasized the point that case is an expression, not a statement. To carry that point further, notice that here I'm introducing very quickly an example of an update statement. This is a DML operation to change the value of a column. So it's not a data retrieval like a select. This is going to modify the content of the database. And notice where we're getting the value. We're going to set the salary equal to whatever this case expression evaluates to. So we're going to update a row in the staff table, and when the department ID of that staff member is equal to theology, their current salary will be multiplied by 1.1. That value will then replace what currently is in salary. That's what the set clause does. But if they're not in theology, we take a different consideration. We say when the department is equal to philosophy, then the salary becomes what it currently is times 1.2, and that replaces what's in salary. Question, why do we have an else? What will the else do? It'll take whatever the current salary is and put it back into the current salary container. Why are we doing that? The reason is if you don't match one of the when conditions and you don't have an else, the value returned by the case expression is null, and what would happen is anyone who's not in theology or not in philosophy, if we did not have the else, their salary would be set to null, and the next pay cycle, if we're using that as the basis for printing a paycheck, they'd be a bit disturbed. So anyway, and if that's not clear, watch the video on missing information where we discuss null values. But anyway, that's why we're making sure some value does get deposited in salary. Even if it doesn't satisfy, the row doesn't satisfy the explicit test that we've included, we will put something in there as a result of the update. Well, that completes the discussion of the searched case expression. As noted previously, I mentioned that there's also something called a simple case expression. We're going to very briefly talk about that, just so that you're acquainted with it. Should you bump into one of these things, you'll know what it is and how to deal with it. Okay, a simple case expression can be thought of as a shorthand form of a search case expression. The syntax is slightly different, but in general, the behavior is the same. In a search case expression, each when clause contains an explicit comparison, but in a simple case expression, you have something called a selector, and the selector is the thing against which a compare will be made with every when clause. So you're going to introduce the selector as part of the introduction of the case expression itself, and that selector, whatever it is specified as being, will be implicitly compared with just a value for an equal condition. Let's take a look at this. Here we're selecting the course number, the name, and then the selector is this thing called cred. Here's the first difference in the syntax. Previously we said case and we jumped right into the when. Here we say case and oh, by the way, the thing that I'm going to compare with all of my whens is going to be whatever the value is in the credit column. Now, the compare is always going to be equality. So when we get to the when clause, we simply put a value and we know that it's going to be tested as being equal to the selector. So this one is saying when cred is equal to 3, then return THREE, although that comparison is implied rather than being explicit as it was with the search case expression. Aside from that, the behavior is the same. If you don't have an else and you don't have a match with one of your whens, then the case expression returns null. But an else is a possibility here. We can include that. Again, the renaming is a very good idea, essentially required. But the point is, it's much more restricted or limited because it's always going to be an equal condition. So anyway, that's the idea on simple case expression to kind of conclude the examples of that. Let's summarize what we've taken a look at. We say that sometimes an exact value cannot be provided to identify the rows of interest to you. That is, as you're formulating a predicate, you don't know exactly the value you want to use, or you intentionally want to be more generic. That's what a major portion of the intro was talking about, pattern matching. Remember, we use the like keyword to say that we're going to be doing this pattern matching, and following the like will be a quoted string which provides the pattern. Again, this applies only to doing comparison or searching of character data. There were two wildcard or meta characters that are part of a pattern or maybe part of a pattern. We had the underscore and the percent sign. Underscore identified exactly one character. Percent sign was much broader. It could be a string of any length, 0, or many characters. Furthermore, when answering what-if type of questions, we can use expressions in SQL to effectively derive values from values stored in the database and retrieved, and then manipulated in some way to derive these new values. Similar expressions can be used when updating the data in the database. Remember that we said these expressions do not have to appear only in the select clause for data retrieval, but they could actually appear as, say, a part of a set clause for an expression in terms of identifying what the value is to be applied. When forming the numeric expressions, we have to be very aware of the data types involved, because the SQL standard makes a clear distinction between what is expected for the behavior of expressions involving exact numeric and expressions involving approximate numeric and expressions of mixed quality, say exact and approximate numeric. So we have to be aware of that treatment. And then finally, conditional logic we saw is available through case expressions. So we covered a great deal of material in this particular video. Now, some of the queries and some of the statements were rather lengthy. So rather than type them in on your own if you would like to try these out, I posted a file called Patterns and Expressions on my website, www.timhartley.com. And we go to that site, go to the menu, and you'll see a link that says Insightful Professor. This will bring you to a page on the website where files for my various videos are available for download. So you can just grab those and get the code without having to type it in. So as these lectures become more complicated, more complex, so do the SQL statements. And you probably don't want to type all of these in from scratch. Especially if you're me. You see how I'm typing them in. I have enough trouble. Okay. So anyway, I hope you enjoyed the video. I hope it was informative and useful for you. And if you appreciate what we're doing here, consider subscribing to the channel, and you'll be notified as to when we post new videos. And once again, thanks for watching.